right, so we're talking about confidence intervals for the mean mu. Let's do one more example. It's really interesting. It's confidence intervals for proportions. Okay. So, this is going back to the 2016 U.S. presidential election, right? The new one is in a couple weeks. Oh, wait. Right, I'm recording this before, so I don't know the results of the election. Anyway. Okay. So yeah, maybe I could do it from 2020 election. Maybe for next year. Anyhow. All right, so this is the data from 2016 election. All right, so somebody made a survey. They found out that out of 688 people, 368, they would vote for Hillary. So 53%. Okay, so that's what newspaper typically tell us is that probability P, right? But what they don't tell you, or sometimes they do tell you the margin of error sometimes, so that you know the half width of the interval, right? That's the margin of error. Okay, so here we are asked to calculate that confidence interval. All right, so proportions are special because they can be thought of as Bernoulli random variables, okay, or binomial, either way. So if we define xi in this way, right? So if you vote for Clinton, I guess, 0 otherwise, then those would be Bernoulli random variables with probability p. Now that probability p is the parameter that we're looking at to compute the confidence interval. So it plays the role of mu before, right? Because it's the expected value of your random variable. That's why proportions are special, because of this fact. And also because of the fact that since they're Bernoulli, we know that their variance is p times 1 minus p. Therefore, it's one case where you can say that we do know sigma squared. This is the only exception to the rule that we never know sigma. Now, there's a caveat here because we would know sigma squared if we did know p. But p, remember, is a parameter like mu. So all we can do is know p hat. Okay? Alright. So given these two, then we apply our formulas pretty much unchanged. Look, we're going to say, so that's your x bar in this case. And then it's the same formula as you see here. Now the only difference is that we know a formula for sigma, right? It's p times 1 minus p. Now, so by the way, so from here you see that from here, let's say, right, that the best estimation of mu is x bar, right? So we can say that p hat is x bar. Something like that, right? And then we use p hat in here instead of p. So that's the thing. It's an approximation, but it's what every textbook does, because we're replacing the exact value p and 1 minus p by their estimators. Okay, but that's how we're going to calculate the variance in this case, right? Because of this. Okay, and that's going to be your confidence interval. All right, or the margin of error, right? The half width is 0.037, right? We could have calculated a 99% confidence interval, okay? And in that case, we're going to get a wider interval, right? The half width or the standard error is margin of error is larger, right? So here's an example that confidence and accuracy, they work in opposite sense, right? Because a 95% confidence gives you a narrower interval, right? The half width is only 0.037. But with a 99% confidence interval, this margin of error increases, okay? So they go in opposite directions. And the reason is because the critical value, right? The value of Z that you use here. This one increases with alpha. No, decreases with alpha. So if alpha increase, then Z will decrease, right? It's because of always this figure like this, right? So if this area is alpha, this is Z of alpha, right? So if alpha tends to 0, you see Z tends to infinity. Okay, so 100% confident interval, in fact, would give you the interval between, let me write it down. The 100% confidence interval gives you an interval between negative infinity and plus infinity, which I don't consider to be very accurate. Yes. So you see, confidence and accuracy go in opposite directions. That's why confidence is such a misleading term. Very good. Now the other ones are very similar to the other ones, so please do it on your own. All right, let's talk about confidence interval for sigma squared. The derivation, luckily, is exactly the same, but just using a different statistic. For sigma squared, we use the c-square statistic, like that has the chi-square distribution, right? So, and we start off with in the same way as before, right? And this equation comes from the definition of critical values, right? That the probability that the statistic, excuse me, will be between these two critical values is by definition 1 minus alpha. Now, just wanted to note that the PDF of the chi-square is not symmetric, and it's only defined for positive values. So it's not like the normal or the t-distribution. So in this case, you need to look up in the table both values. You cannot say, as we did before, that one is the negative of the other. So we need to look up these values separately. We'll do that in a minute. Okay. And yeah, this is a typical shape of a chi-square distribution. All right. And then we proceed similarly, okay, as the other one. So we're going to replace the definition of c-squared right here, and then we're going to solve for sigma squared, okay? And when you do that, you're going to obtain these intervals. Now, the formulas are a little different, right? It's not something plus or minus something, because things are not symmetric here. So this is how they read. So the two-sided intervals, they always have x of alpha over 2, 1 minus alpha over 2. The lower confidence interval, remember, they all have x of alpha, because the whole probability alpha goes to one side. All right? So really, same concept. The only difference is that the equation looks a little different. And then the interpretation is going to be the same. Okay, so very simple one. Yeah. Suppose that the sample size is n, and we know they're giving you the sample mean and sample variance. What is the confidence interval, 95% confidence for sigma squared? Very good. So here, let me show you how to obtain these values from the table, which are the only ones you need, really, right? So we're going to go to this link when we talk about the chi-square. And I try to click it. All right, there you go. Okay, so that's your table. Very similar to the T table. Okay, let me try to zoom in here. All right. So first row, is degrees of freedom, which is n minus 1 in this chapter, right? And then you have all the x of, it could be alpha over 2, could be alpha, right? 1 minus alpha. But yeah, the subindex refers to alpha. Okay? So for example, let's go back to right here. Oops, yeah. All right, so n equals 9. Really, that's the only number you need, n alpha, which is 5%. Okay? N equals 9, n alpha. Now, we're going to do all intervals. So the two-sided and the one-sided ones. All right, so let's start with the two-sided where we need the alpha over 2 terms. Okay? So, we said sample size is equal to 9, right? So 9 minus 1 is 8, so we're going to look at this row. Okay, I cannot select, but that's okay. All right, so focus on row with 8 degrees of freedom. Okay, alpha is 5%, but for two-sided, we need 1 minus alpha over 2 and alpha over 2, right? So alpha over 2 is 0.25, it's right here. Oh, I can't select. So the number that we're looking at is that one, 17.5, let's see. Right here, okay? So that's alpha over 2. And then we look for the other one, 1 minus alpha over 2, so 0.975, I guess. Right here, 2.18, all right? That's the 2.18 right there. And these ones we're going to use for the equations of the two-sided intervals. Well, I should have stopped right there, right? And these two, this goes there and this goes there, right? All right, let's find the x1 minus alpha now. So alpha again is 5%, so we look for 0.95, which would be this one, right? 0.95 is right there. So 2.733, there you go. Same thing for the other one, so we're going to look for chi-square of 0.05, which would be right here, 0.05, right? And 8 is 15.507. All right, so that's how we get those values from the table. And then all we need to do is evaluate, right? Because we know n, we know s squared. Yeah, there's a mistake here. These all should be lowercase. Okay. Right, because it's a realization, and we already know that its value is 11.7. Okay, so that's how we obtain these confidence intervals. Now they have the same problem interpreting these numbers, right? Which I don't find very useful. But anyway, we need to know it. All right, this topic is a lot less controversial, right? Some people like confidence intervals, I don't. Doesn't mean you have to not like them. But hypothesis testing is a lot less controversial. Now it's very similar, you see that we can test kind of the same problems, we can answer it in both ways. But anyway, so let's motivate with a basic example, all right? So let's say we're producing laptops, right? And the throughput is normally distributed, right? It's like number of laptops per hour. It was normally distributed before we did an improvement, okay? So based on the history of the system, you know that you produce an average 20 per hour, and that's your variance, 100. Okay, and then you implement an improvement, okay? And then you want to see if it was successful, right? Effective. So to do that, you're going to take another sample and do some calculations. And these are the calculations we're going to explain here. All right. So the setup is always the same. There's always a null and an alternative hypothesis. So for the null, you have typically you don't have any choice. It's just that the mean value or the parameter of that you're trying to hypothesize. Okay, it's like the default value of the parameter. So in this case, it's mu is the parameter that you want to see if it changed after the improvement, right? It's the mean production rate. So the null hypothesis is nothing happens. Let's say that the new mu, it's equal to the old mu naught. That's going to be your default hypothesis, which will be true in the whole process. That's very important. We're going to assume that H naught is true. Okay? All right, and for the alternative, you have three choices. Pretty much like in confidence intervals, is it two-sided or one-sided? Here's the same thing. So option A is two-sided because you say mu is not equal to mu naught, and that's going to have two sides. And then you have the one-sided alternative hypothesis. Either it's greater or it's less than mu naught. Now, which one to choose depends on the question being asked. So here, for example, we want to know if there's an improvement. Okay, so we really want to know if the new mu, so just mu, is greater than mu naught or not. So for this particular question, since it's an improvement, I would choose alternative B here. Okay, because that's what you want to, that's what you would like to test, really. Okay, in some questions, they are only concerned if mu is not equal to mu naught. Like when the question is, was there a significant change? But you don't know if the change is improvement or the system got worse. Okay? So, yeah, how you choose your alternative hypotheses will depend on the question being asked. And in general, what you want, or not what you want, this gets interesting whenever you're able to reject the null hypotheses. Because then you learn something. You learn that the alternative hypothesis might be, in fact, true. All right. So let's do a particular example. Let's say we have a coin with probability mu of coming up tails. Okay, so we call it P, but don't we call it mu. All right, so in this case, you want to know, is it fair or not? Okay, so alternative, well, null hypothesis always mu equals mu naught. And mu naught is being fair now, right? And fair means probability 1/2. Okay, now, the test of fairness is just that mu is not equal to 1/2. Because you don't care if it's loaded towards the tails or the heads. Now, if the question was, is the coin biased toward tails, then that's going to be your alternative. Okay? So the alternative always depends on the question being asked. All right. So the basic t-test, it starts with the definition of the t-distribution, or the t-statistic rather, right? The same t-statistic with the student's tn-1 distribution. Okay? Now h naught is always going to be like that, right? And it's always going to be assumed to hold true. All right, so if it's true, then we have this situation. Now, if you compare these two, the difference is minimal, right? It's just instead of mu, we wrote mu naught. But it's kind of significant because mu naught is a number, right? That's given to you in the problem. So what you do know is that x bar minus its real mean is the t distribution, right? But now the real mean, we're assuming that it's mu naught. So if mu naught is true, then this t is true. Okay? Which comes down to assuming that h naught is true all the time. Okay. And now the key idea of the hypothesis testing is the following, is that if you observe a realization of this capital T, all right, and the way we do realizations in statistics is take a sample and evaluate this formula, okay, and that's we're going to call it little t naught, all right, so lowercase t naught, and everything is in lowercase here because everything is from sample, so x bar and s, okay. Now we're going to observe a realization of t naught, of capital T. Now, the distribution of t is right here, and it's like the normal 0, 1, pretty much, centered at 0. Okay, so this being the distribution, you expect t naught to fall, you know, where all the probabilities are. Like where the highest probabilities are, right? So you expect t naught, if it's gonna be t distributed, as said right here, then you expect most realizations to fall within this area, you know, near the mean of it, which is 0, right? Okay, and not surprisingly, we're gonna call this area 1 minus alpha as before, and then the two tails will be alpha over 2 as before. Right, so these are going to be the critical values again. T of alpha over 2 and minus, or negative, T of alpha over 2 right here. Okay, so that's the key idea, is that when you have a distribution, you expect any realization of that random variable to be close to the mean, like that. And that's really the criterion we're going to use. And now the parameter alpha, so 1 minus alpha in this case, is that probability of being close to the mean. That's what it means in this case of hypotheses. Okay? And it's very simple. The test is very simple. We're going to say if the realization of the variable t falls within this interval, then we're going to accept it. We're going to accept the null hypothesis. But if this realization falls very far from the mean, like around here, let's say that's t naught in this case, then we're going to say, it looks like this random variable might not come from this distribution, and therefore we're going to reject h naught. So it could fall here or here, right? So away from this interval. So in this interval, we're going to accept h naught, right? Because the realization, let's say we obtain is 1.3, right? And typically these critical values are around, 2 or 3, right? So between -2 and 2 or so. So 1.3 would fall inside the interval, so you would accept the null hypothesis. But if it were to fall outside, then we're going to reject. And that's pretty much it. Once you have this key idea, it should be straightforward. Okay, so we can explain this with these better figures, I guess, right? So let's take this example, the one we're looking at. So the alternative is that they're not equal. Okay, so yeah, this is the acceptance interval because it's close to the mean, right? So yeah, here you have, this is the two-sided test, right? Now, these are the reject regions, right? When you fall in these two areas, right? Because you're far away from zero, which is the mean of capital T, right? And in the middle, colloquially, you can say accept H naught, but we rather say we do not reject H naught. Okay, so in statistics, you always want to give answers that leave room for error, because there's error regardless. So typically, you would say we didn't find evidence to reject H naught. You would say something like that. Right, but here in lectures, I'm just going to say accept and reject H naught, okay? All right, let's look at the figure in the right. So here the alternative hypothesis is that there was an improvement to the system, okay? So that the new mu is greater than the old mu naught. So, and remember, H naught is always mu equals mu naught, so, and by default, we assume that is true. So, if our realization T naught fell here, then we would accept it, right? Because it's in the acceptance region, which is now from here on out to that way. And then rejection is in that direction. All right, and then for the other alternative hypothesis, mu less than mu naught is going to be the mirror image of this figure, okay? So here you have a summary then, when to reject and when not to, right? So the graphical summary, and this is kind of the equation summary, if you will. Now, typically we're going to use this alternative hypothesis, and the rule of thumb would be that the absolute value of T naught be greater than the critical value if you want to reject H naught. Right? Because again, it's symmetric with respect to zero, so you don't want to be in these tails. Okay? All right. Okay, let's do this example. So we collect the sample of speeds of vehicles. All right? So let's see how many there are. 1, 2, 3, 4, 5, 6, 7, 8, 9. N equals 9 here. Okay. And the speed limit is 45 miles per hour. And, okay, first determine the interval, then test the hypothesis. And then sample size. All right, so we know how to do confidence intervals, so let's concentrate on part B here. All right, so for the intervals, yeah, we know how to do this. Now, this is new. So, here the question is, test the hypothesis that vehicles are speeding with alpha equals 5%, okay? All right, since that's the question of interest, the question is, are vehicles speeding or not? Okay? The way we answer this question is, all right, no hypothesis always is mu equals the default. Now the default is 45 in this case because that's the speed limit. Okay? So if you're going at 45, you're fine. Now, the alternative hypothesis is where really you answer the question. Okay? So are they speeding? So, and the event of speeding means that the speed is greater than 45. So that's why we use greater than. Now, notice what we did here. The question is about is a general question. It's like, are vehicles speeding, right? It's not any particular vehicle. So the way we interpret that question is the mean of vehicle speeds greater than 45? That's what we're saying. So all the testing that we're going to do will refer to the parameters of the distribution either mu or sigma squared. Okay? But, so bear in mind, the questions are always posed in terms of the random variable, not about the parameters of this random variable, right? But the way we do hypothesis testing is by using these parameters. All right, so H1 is greater than 45 because we want to know if they're speeding. Okay, so from the table, alpha, so it's a one-sided test, so this is T of alpha, so it's 183. From the table, we know how to do that. And then simply we compute the value of T naught, like that. And we obtain 1.27. All right, so this is a situation where this is 1.83 and this is negative 183. And T naught is somewhere in the middle, right? It's in the acceptance region. Right, so there's no evidence to reject H naught. So we cannot say that vehicles are speeding. Oh wait, here I should have put this because it's a one-sided. Yeah, so it's like that. The whole area alpha here is to the right. Yeah. All right. So we're in the acceptance region. So no evidence to reject this guy. Okay. Very good. Now notice we have here the confidence interval. Oh no, never mind, because this one's two-sided and one-sided. Alright, never mind that. Okay, so we failed to reject H naught. C sample size calculation, we've done this before. So nothing new here. Alright. So now let's give alpha another meaning. So we call it the significance level for confidence intervals, right? And 1 minus alpha was the confidence level, and confidence is this word that is used in lieu of probability to kind of cause more confusion. Let's just say that. All right, but alpha in the context of hypothesis testing, it's known as type 1 error also. Okay? So, these are the definitions of type 1 and type 2 error. Okay? And we're just going to be concerned with type 1 error in this course. Beta, we're just going to define it, but we're not really going to use it. Okay? Alright. So, type 1 errors is rejecting H naught when it is true. Okay? So you can do this table, right? First, let's assume that H naught is true for a minute, okay? And then your test, which is, right, it's evaluating T naught, example here, and seeing if you reject it or not. So, you could reject it here because it would be possible, right? Even if H naught is true, it is possible that a realization will fall in the rejection region. So it is possible that a T naught would be in the rejection region even if it comes, or even if H naught is true, so that, the mean is in fact mu naught, right? It is possible, it's unlikely, right? And the likelihood of that is alpha, right? Because it's the areas of these curves that, under this curve, that is alpha by definition, right? So that's why it's an error. And again, it's because if you have a distribution, most of the realizations will fall in this interval, but 5% of them, or alpha percent of them, will fall in the rejection region. right? Even though they come from the right distribution, and you're saying no, because my test is like that. So that's the error of the test, is that you're gonna reject the null hypothesis even though it is true, right? So that's our new interpretation of alpha. And that's why you want to keep alpha small, right? And 5% appears to be the number of choice. All right, and now the other type of error, so it's when H naught is false. Let's say that you do know that it's false, okay? And then you do not reject it. So that would be the type 2 error, okay? All right, but again, yeah, beta, it's also known, 1 minus beta is known as the power of a test. You might have heard the word. But again, we're not going to talk about it very much. Only alpha. All right, let's talk about the p-value. This is a very important concept to know because any software package in statistics will output a p-value and also a t-value, the t-naught value that we saw. But they go hand in hand. Some people like to use more the p-values. I like to use the t-values, right? But we need to know both. And they're very related, okay? So, the p-value, you can say that is the probability of the statistic, in this case t, taking a value at least as extreme as the observed value t naught. What do we mean by that? All right. So this is alpha is right here, right? This is t of alpha. Let me zoom in for you. And this is t naught. Okay? Now, this area from t of alpha right here is alpha in blue, right? Because it's to the right of t alpha, right? Okay. Now, if you take your realization t naught, put it in there, and then calculate the area, then that's your p-value. So, in the case of this alternative hypothesis, the p-value is the area to the right of t naught. And again, t naught is the value that you obtain from the sample. Okay, so notice, imagine that you move t naught towards t of alpha. All right? So, and when t naught equals t of alpha, you see that the p-value and alpha are the same. Right? And that's the idea of as extreme as, right? So if you want to be as extreme as, that would be t naught equals t of alpha. Right? Now, you could be even more extreme. And then t naught could be here, right? And in this case, the probability to the left of t naught, to the right of t naught would be less than alpha. Okay? So, looking at t naught or p, it's the same, gives you the same result. It's an alternative. So you can use p-values or t-values to make your conclusions. Okay, so let's look at intuition 2 here. Equivalently, so the p-value is the smallest level alpha such that we would reject the null hypothesis, right? So what it's saying is that in this case you could make t of alpha go to t naught, right? So if t of alpha, you say you move it to the left here such that it coincides with t naught, then the p-value and the alpha would be the same, right? So So in that case, it would be the smallest alpha such that you would reject, such that T naught would be right in the verge between accept and reject. Okay. All right, so hopefully it makes sense. So again, I think the best definition is the first one. It says the area, so in the case of this alternative hypothesis, going to be the area to the right of T naught under the curve. Right? So accepting H naught would mean that the p-value is larger than alpha. Right? So I think it's in the next slide. Yeah. Right? So when the p-value is less than alpha. Right? And you see that from the figure. Right? So when T naught is in the acceptance region, which is from here, then the p-value, which is the gray area, is going to be greater than the blue area, which is alpha. Right? And conversely, when T naught falls in the rejection region, then the p-value would be smaller than alpha. All right? Okay, now, for the two-sided case, it's a little bit, it's the same concept, but we're going in both directions at the same time, both to the right, right? So the area to the right of T naught, and also to the left of negative T naught, because these things are same. Negative T naught. You see, you have these. So the p-value is, and this is a formula to express that. You take the minimum of these two probabilities, right? And it's the area, that's the area to the left of T naught, and that's the area to the right of T naught. And you multiply by 2 because it's symmetric. Now, don't worry about the formula, though. P-values will be given to you if we ever use them. Yeah, that's the thing about p-values, is that it's really difficult to compute them by hand, because typically all we have is the t-table. So, yeah. So by hand we don't compute p-values. We compute t-statistics. So in that way it's easier. Very good. Yeah, and this formula, we didn't comment on it, but it's just the area to the right of T naught, like in here, right? Probably if T greater than T naught is that area. Very good. So that's your p-value. So this is how we are going to reject H naught. And these are three equivalent ways, okay? So first is the t-test, when it falls in the rejection region. Second is the p-value, when the p-value is less than alpha, right? Less than alpha means that you're in the rejection region. And finally, which we haven't discussed yet, we can test hypotheses also using confidence intervals. And I guess that's the only good use of confidence intervals that I see. But that's just my opinion. Okay? All right, and it turns out that if you compute the confidence interval, this one, right, in the way we did before, okay, and that if you observe that the value mu naught, right, the one that you're testing in your H naught, your null hypothesis, right, that value mu naught, if that value doesn't fall in your confidence interval, okay, then you can reject it as well, because they're equivalent, and you can follow this thought process. Okay, so yeah, this is how we reject with the t-value, right? If the absolute value is greater than the t of alpha. Yeah, here I should have t of alpha there too. Okay, so that means that T naught is not in this interval, right? These are equivalent statements. And then what we do from here to here is replace the what T naught is. Remember, it's little x bar minus mu naught divided by s square root of n, right? And so we replace that here, and you obtain that interval. Very good. So you have three ways of doing it, with t-test, p-value, or confidence interval.